energy buildings. Then we will talk about LEAF House and the LEAF Lab. In particular, we will describe the construction process. We will show the sensor data and the building automation systems that are present in each of these buildings. Then we will show performances and also studies and future works related to these two zero energy buildings. And then we will draw some conclusions about it. A brief introduction. The LEAF House was built in 2008 and it is a smart residential building. It is carbon neutral and it has high energy efficiency. And the interest in high energy efficiency building continued in 2013 when Nochoni Group built the LEAF Lab. And this industrial building is the first connected industrial building ever built by the Nochoni Group. And both buildings are located in Angeli di Rosora. You will see here in the map, and it is located in the region of Marche, in the central part of Italy. And in Angeli di Rosora is also where the Nochoni headquarters is located. So the academic seconded partners will come here to the Angeli di Rosora during their secondment. The idea behind the LEAF House is to start from the traditions and our roots, so from the typical farmhouse in the market that was seen as an autonomous and sustainable microcosm where every resource was exploited and nothing wasted, we arrived to the LEAF House. And here you can see a picture of this. We can't hear you. Hello?
Hi.
Hi. Can you hear me?
Yes, we can hear you.
Yes, so who can't hear me? Energy Group, we can't hear you. I think they're having some issues with the audio.
Yes, we know, but I have sent them some instructions, but unfortunately the WebEx today has some problems, so we have to start the presentation. I will help them to connect.
Okay, shall I continue or?
Yeah, should continue.
Okay.
If they want, they can hear the presentation afterwards, the recordings.
Okay, great. Then there's this video about the LEAF House. So yes, can you please load the video, Kostas?
I'm now doing it.
Yes, thank you.
Okay, now I'm playing the video.
Great.
The flagship of the community. Laura, please
yes?
Move to the next slide.
Okay. We will share the video eventually later on because
we share it.
Yeah, no, but there was only sound and no video. And the video came really, really late, but okay.
Okay.
Let us continue with the LEAF House. So this is a picture of the front side of the LEAF House, and as I already told you, it is a residential building, and the idea was to build it in a way that we minimize energy consumption and emissions. It comprises 6 apartments, and then we have in 4 apartments there are 8 persons who are regularly living, and then we have 2 guest apartments. The LEAF House is an open laboratory, so we have many researchers who have been working on it since 2008, and many changes and upgrades have been done on the LEAF House. The project was supported by the Loccioni Group, and it was also sponsored by many partners, both industrial and academic. This is the LEAF House, so you have this view from the front and also from the side. We have 4 garages, and you have it here, if it is working. Yes, so here you have this 4 garage, and then you have also 2 dedicated parking spots on top. Then you have also photovoltaic installations in the roof, and you have these 6 apartments. The building is south-oriented, and the ratio between the south length and the east facades is 1.34 in order to maximize the solar gains during the colder season. And on the roof you have solar thermal panels and the balcony also. In this way also the design of the roof and the balcony top was designed to behave as solar shadings during the hottest months. About insulation, you have this plot over here. So we have, from the outer surface, we have 20 millimeters of plastic plaster for coating. Then we have 180 millimeters of insulation panel, which behave more or less like 1.5 meter of bricks. And then we have 15 millimeters of cement mortar. Then we have 300 millimeters of Poroton bricks, and then we have 20 millimeters of mortar gypsum plaster. This is the insulation structure of the LEAF House. With reference to the lighting systems, in the rear part of the house, which is facing north, the sunlight arrives carried by solar tubes, and you can see this on the picture that is in the presentation. And also in each apartment, tenants are allowed to, through the display in the home automation system, they're allowed to control and switch on off lights in the apartment. The LEAF House also has a water collecting system and treatment. So the rainwater is collecting in energy group. Can you please turn off the audio? Yes, great. And the rainwater is collecting the tank, which is dug under the garden, and then this water is reused for domestic purposes and for irrigation. And this caused a high saving in water consumption, and I will show you the performances later in the presentation. And the water is also pre-treated in the kitchen, and so sink have 3-way valves, so you have hot water, cold water, and also drinkable. And in this way, tenants can drink tap water, and this avoids buying plastic bottles also for recycling it. So it is a very good idea. This is the thermal central unit in the LEAF House. This is an old picture, but you can see on the right there's the air handling unit. Then you have the control area, and then you have the geothermal heat pump on the back front, and then you have on the left side the hot water boiler. Basically, the LEAF House has one geothermal heat pump, one air handling unit, then each apartment has radiant floors for heating and refreshment, and then you have a photovoltaic installation, rooftop photovoltaic installation. With reference to the air ventilation, you can see in these 2 pictures in the presentation. the outer air, which is usually colder and hotter in the winter and summer. It is taken from the outside, and then it is naturally preconditioned through this underground path of about 10 meters, and then this air goes to the air handling unit, and then it is heated or cooled during summer or winter time to each apartment. Sensor data and building automation. In the LEAF House, we have more than 1,000 sensors installed. These sensors are related to indoor comfort, for instance, temperature, humidity, and CO2 levels. And then we have sensors also for thermal and electrical measures, and then also sensors for energy consumptions, of course, and also to monitor the rainwater level in the collectors. With reference to the building automation, as I already told you, each apartment has a display that enables tenants to set the desired temperature in the apartment. So if they decide to have 20 degrees or more in the apartment, they can also monitor lights, so to check if they have lights on and off in a specific room in the apartment, also to check if windows are open. And they also monitor the energy consumption of the main electrical appliances in the apartment. About the performances, so as I already told you, many changes and upgrades have been done over the years in the LEAF House. And of course, this affects the annual energy consumption. For instance, in 2012, we introduced electric storage in the LEAF House. And you can see that then in 2012, the energy produced self-consumption was about 58%. And before, of course, this was not possible. Unfortunately, the storage, let's say that it wasn't operated until the late 2014. And now we are thinking about replacing it with another kind of storage. But at the moment, we don't have an electric storage at the LEAF House. But these data are related about to late 2014. With reference to water consumption, first of all, we need to say that in Italy, a family consisting of 3 people, the water consumption is usually 130 cubic meters. In the LEAF Houses, you can see in this table below, in 2012, the water consumption was 229 cubic meters. And you can see that the water collecting system, the rainwater collecting system, caused the high water savings. And that was also, it's almost the same in 2012, in 2013, and 2014. So we can say that this water collecting system caused a high saving in water consumption. What has been done on the LEAF House over the years? So many journal conference papers, then a master thesis and also PhD thesis, mainly about modeling and advanced control techniques applied both to one single apartment and to the overall building. And also the LEAF House participated at the task force in net zero energy buildings by International Energy Agency. Another case of zero energy building that I will talk about is the LEAF Lab. This building was built in 2013 and it was fully operated in 2014. It is an industrial building and it is connected, so it is exchanging energy with the grid. The architecture and engineering choices ensure comfort of people who are constantly working there, low management costs. The investment also was not so high because it was 20% more than the construction of the traditional building, 6,000 square meters, and the LEAF Lab is A+ energy efficiency. And also the annual energy consumption is about 4 kilowatt-hour per cubic meter, and the building is completely natural gas independent. About the construction of the LEAF Lab, so we have a rooftop PV installation of 235 kilowatt peak. Then we have both electric and thermal energy storage, and in this way, these storage systems enable different kind of energy fluxes optimization, for instance, peak shaving and time shifting. Then about thermal electrical equipment, we have pre-cooling, because during the night when we have that the external temperature is lower than the internal one, then we have this air exchange, and we have, for the offices, we have a mechanical exchange, while in the production area and in the warehouse, we have a network exchange. So basically, automatic shades open. And this allowed consumption savings up to 10% for cooling, of course. And then we have also natural cooling, because during summer, the energy demand for conditioning in the office area is mainly satisfied by using 10 minutes of groundwater. And in this way, heat pumps are not used for this purpose, and we have savings up to 20%. The LEAF Lab has also 3 groundwater heat pumps, and with reference to the lighting system, we have LED dimmable lights, presence detectors, and illuminance sensors. So we have these artificial lights, dimmable, and they're regulating according to the external daylight. And the presence detectors, let's say that it enables lights to switch on and off, and energy consumption is usually reduced up to 66% in this way. Sensors, data, and the building energy management. So we have many sensors installed in the LEAF Lab, of course. Mainly they monitor the weather conditions and also internal comfort. For example, the lighting comfort, temperature, and also to ensure the proper air ventilation. Data are collected through the proprietary Loccioni web-based platform, which is called the MyLEAF. And this web-based platform enables users to monitor, analyze, and download the data consumptions and also data from sensors. In this picture, you have this MyLEAF platform. You can see on the left side, you can select which measure you would like to plot to see. And then you can plot on a desired period of time, and you can also do some statistics analysis on this data. You can download them in many formats. And this web-based platform is actually, you can access to it by a tablet or a normal laptop. With reference to the building energy management system, it's developed and implemented on a proprietary Schneider software platform. And you can see this, for example, is the main display. So you can select if you want to control a lighting, or if you want to control the water system, or if you want to control the air handling unit. And also, for example, this is the lighting control. You can see that the control is implemented in a kind of Simulink layout. It's not really Simulink, it's software developed by Schneider, but it looks like Simulink somehow. And here you can implement your control techniques and apply it to the LEAF Lab. Performances of the LEAF Lab, as I already told you, the LEAF Lab started to be fully functional in the second half of 2014, so these performances are mainly given by forecasting. But let's say that the energy consumption for LED is about 2.2 euro per square meters per year, while the traditional lighting system is usually 3 times this value, 6.6 usually. The peak power of the LEAF Lab is 235 kilowatts, and the energy production is usually 280 megawatt hour per year. So let's say that the 70% of the time we're not acquiring energy by the grid, because we're self-sufficient. The electrical storage is 224 kilowatt hour, the capacity, while the thermal one is 450 cubic meter. Also savings given by the thermal equipment installed in LEAF Lab compared to the air heat pumps is 30%, 35%, and savings compared to high efficiency boilers instead is 55%. And I would like to remind you that the construction of the LEAF Lab was almost 20% more expensive than the construction of traditional buildings. So you can say that these high energy savings are, they're huge compared to initial upfront costs that the LEAF Lab costs. So conclusions, the LEAF House and LEAF Lab demonstrate that proper architectural engineering choices ensure, first of all, high energy savings. and also internal comfort, because in the LEAF lab, people are currently working there 5 days per week, and also in the LEAF house, people are living there regularly. Consequently, the academic partners, second to AEA, they will have the chance to work with the LEAF house and the LEAF lab, and also to manage and analyze all the data available from the sensor installed. In the LEAF house, the monitoring activity started in 2010, even 2009 we have some data, and in the LEAF lab everything started in 2014. Thank you for your attention, and Merry Christmas. This is over with AEA. Do you have any questions? Hello?
Just one question from our side.
Yes.
Have you considered the possibility of to apply some, let's say, innovative component as a test bed for innovation in specific items? So, for example, storage or cooling systems, things like that, or are you using only out-of-the-shelf units?
But we are using storage. I mean, we have
some experimental ones. I mean, is this a place where you are just putting together things that are existing on the market, or the LEAF house can be intended as a test bed for innovative systems?
Yeah, sorry, I didn't understand the question. Yes, I mean, it's open for innovative items, of course. Actually, a few years ago, we installed a nitrogen storage system in the LEAF house.
Okay.
But
it didn't work at the end, but the purpose was to test and verify the functionality of this innovative storage. So yes.
This could be something to discuss if there is an interest in cooperating in using the LEAF house as a test bed for high maturity level systems that can be tested in a real environment.
Yes. I mean, this is fine by us. I mean, as I already told you, the LEAF house was built with as an open laboratory somehow. So, of course, we are open to test innovative solutions.
That's great. And you said that the data coming from the house are available. So it would be interesting to have access to this, even if we cannot make a national exchange. Because for us it will be interesting to verify the typical data of this house to understand what we can test there, and if we can test something there, because there are, I think, specific data related to the environment, the kind of people that are living there, and so on.
Yes, we have many data coming from both the LEAF house and also the LEAF lab too. So I might say that we are monitoring almost like at least 5 years, because from the LEAF house till now. So we have many data. So if you are interested in getting some of them for simulation, we can talk about it.
That sounds great. Yeah, thank you.
You're welcome. Any other questions?
Okay, thank you a lot for the good presentation. The floor goes to Fabio from AEA in order to make his presentation, sorry.
Yeah. Are you going to upload this, or I have to do something?
The presentation is already uploaded.
Okay.
It's right to the meeting info.
I have to do something to show it, or are you going to? Okay.
Here it is. And
perfect. So I can. Now I think I can go to the In this way? Okay, fine. Okay. Here we are, me and Filippo Paredes, and I think we will share the presentation. It's a way to not to have always the same voice in the webinar. The main objective of this presentation is to introduce some of the technologies that can be applied in zero energy building, because the number of technologies and their combination is very wide, and we will try to give some hints about the maturity level and the market perspective. Of course, this will be a very short overview, so information will not go into deep, and some of the consideration about the market perspective, of course, wouldn't be complete. But I think it will be useful to have this list of all the possibilities we have collected in the presentation. Just an holistic overview of the concept, then we will present some energy harvesting technologies that can be applied at zero energy building scale, some building integrated storage system, both electrical and thermal, and devices to convert the energy into useful application for the tenants of the building, and just a very short introduction to the market innovation in the control system and smart appliances. Let's go to the first. To the first slide about the overview, just to say that the combination is very, the technologies that can be combined are quite many. The approach should consider them as a wall. So if you are going to change life, the presentation of the LEAF House has been very good for that, because it's clear that you have to think to the building as a wall, as something that will generate and use energy, and that can save energy in an holistic approach. Everything that is a waste from one process could feed a new process, and everything that is around the building can be used to improve the efficiency of the building. I appreciated very much the suggestion to go back and thinking as the old farmers did, because in farmhouses, in our traditional country houses, they were using almost everything. So they had an holistic view. It was something in their behavior, not something that was coming from science and technology. But I think this is the right attitude. And to go a little bit too deep for that, we can work in insulation, of course, in optimizing the lighting, both the natural and the artificial one, in reducing the consumption and recovering energy. We can generate energy, we can optimize the use of that, but we have to take care about the human behaviors, because if you don't change the attitude of people that are using the building, the system will not be optimized at all. It will not work as an independent technological artifact, because there are humans that are using it. And so all the process is very difficult to be standardized, because you have to deal with the location, with the tradition in building industry. Sometimes, especially in Europe, you have to refurbish existing buildings, and you need the cooperation and the commitment of people. To generate energy, we have again a very wide range of solutions. Key issues are the downscaling, because sometimes they have been developed for larger context, and we have to bring them into the building context. They should be flexible, integration should be easy, and they must be cost effective. Mostly we depend upon the solar energy with different solutions, from the wind energy, the biomass transformation, from geothermal resources. If we have water, we can use micro hydroelectric generators. And we would consider in this approach also the micro cogeneration and fuel cell, even if the fuel is coming from outside and it might be fossil fuel, but as both of them are a way to optimize the generation and delocalize the generation, we suggest that these technologies as an interesting one for the approach. About the solar thermal collectors, we have essentially three kind of collectors that can be integrated: the unglazed ones, the flat plate, and the evacuated tubes, and they would be applied accordingly to the temperature that we want to reach. So is the gradient above the ambient temperature that is relevant, and the solar radiation. And according to what we want to get from the sun, from the solar radiation, we have to choose the right one. Very cost-effective and easy to install systems as the low temperature systems that are made by polymeric materials. They have no glazing, they are flexible, they can be just put as a layer on roof. They will work at 10 degrees above the ambient level, and usually you can apply them for preheating, for swimming pools, or just to help the whole building to get energy from the sun and then post-process it as with other systems. Technologies at a full maturity and cost is about 150 euros per square meters of collecting surface, and with 10 degrees of delta T, they are working quite well. So we should consider them for zero energy building as a pretty solution to apply. The medium temperature solar thermal collectors are working up to 50 degrees above the outside level. They are widely used for heating water, for integration in air climatization, and the technology is fully developed with some different quality and different materials, but more or less the price is moving around 200 euro per square meter. So the cost is a little bit more than the polymeric and glazed ones, but of course the flexibility for the application is better. Next step are the vacuum pipes. These are the first ones to have a dedicated optic. It's usually a CPC, so a small parabolic mirror. Typically, it's a metal mirror on the back. They can go up to 150 or even more Celsius degrees. But of course, the efficiency is going down with the outlet temperature. They are the first ones to be considered to drive some solar cooling units, because the quality of the heat is enough to drive absorption or absorption cycles, and technologies at a good level of maturity, and now the competition is about price, and they cost about 20–25% more than flat ones. Here we are in the most innovative collectors. The one you see in the picture is the one we have built close to the Cyprus Institute a couple of months ago. That's going to be in operation in months, and in this case we see the downscaling of solutions that are typical of larger collection system as the CSP fields. They are quite interesting for industrial heat application, or for settlement to support house settlements as a distance heating, district heating or cooling approach. We can go up to 300 Celsius degrees using appropriate heat fluid to drive the heat inside the house or the building. We have some demonstration units and some early commercial sites. Cost is about 300 euro per square meter of mirrors. This was for thermal. Now let's just make an overview on photovoltaic and applications. We can use typical commercial PV modules. Now they went up to 15% of efficiency. Some modules are claiming up to 20% for double-sided panels. The installation is very flexible. We can put one module or 1,000 modules, and the installation process will be the same. They will last for 20–25 years, and I want to say that typical rooftop installation now is costing 2 euro per watt of electrical peak power. That's 3 times less the estimation we had 6 years ago. So now they are really competitive, and a competitive and flexible solution to bring house independent for the energy generation. If we want something more aesthetic or more adaptable to the roof, we can use the flexible PV strips. They are made with thin film deposition technology. They can be integrated in roof parts or in facade parts. Efficiency is quite lower. We go down to 6–8%, but there are forecasts in roadmaps, in technology roadmaps, to reach 12–14%. The efficiency is low, the cost effectiveness is low, but we can verify that cost should fall to about $1, or if we want to consider €1 per watt of peak electrical power in years. This kind of flexible panels made with the synthesized cells generation can be even integrated into aesthetic parts of the building. This is very relevant because the aesthetic factor is a very important factor in acceptance of technologies in building industry. So we can make very efficient systems that are not accepted by both by designers and both by owners of the buildings, and this will affect the roadmap to zero energy buildings. So these kind of solutions are very interesting because they are mixing the two points. They are improving efficiency and they are considered nice to be applied. Most of these systems are at pre-commercial phase with some relevant demo installation. And, again, I'm showing you a system, the glass block that has been proposed by one of the startups we have here in Palermo in a project for zero energy buildings in Horizon 2020 with some of US partners. And finally, a technology that we want to consider for future improvements is the concentrating photovoltaic. Now we have an efficiency of modules up to 35%, and the forecast is to achieve the 40% in 5 years. We need the 2-axis tracking because they work with direct radiation, so the system is more complicated than the fixed solar systems because you need some mechanics and some electronics. Optic is a sensitive issue because the optic should be of high quality. But the advantage is that we use more regenerating materials because the surface of active surface is reduced quite much, and the system can be combined with heat production, and the overall efficiency for integrated building systems of CHP could go above the 80%. So it's very interesting because this would be one of the most effective combined heat and power production for zero energy buildings available. The forecast of price drop, the picture is from Fraunhofer, is that in 2030 they suppose that PV is almost at the plateau, so it will not drop anymore, about 20%, and CPV potential is quite higher, so they should be mostly overlapped in 2030. Wind turbines, so let's go to wind as a generation system. They are quite complicated to be integrated in building environments because they are they need a stable wind. There are some solutions to integrate them on roofs or into some civil structures as roads or bridges and so on. Cost of generation is interesting if you consider that this generation is subsidized by some feed-in tariff or some other solution, some other support. They usually are ranging in 120 kilowatt of generation power. Another source that can be available around the building is biomass. biomass can even be generated by waste. Each of our houses or communities are generating waste. We consider with interest these approaches that are moving the biofermentation, so the biomass digesters, in the direction of small and house or community integrated units. The picture I'm showing you is a startup from Israel. They have patented this very small system and they are cashing money on Kickstarter in these days, or in Indiegogo, I think. It will cost about 1,000 euro, and it will process the waste, organic waste of one family, generating 0.6 cubic meter of natural gas per day. So you can use your waste to cook the next food with which you will generate the next waste, and this circular approach is very interesting to be developed in future. Of course, the easier way to process biomass is to burn it. These systems are very cost effective. They are quite at a quite good level of maturity. They will cost about 100 euro per kilowatt of installed power, of thermal installed power. And they can be easily integrated with solar thermal systems. So where you have biomass, this is a very good approach to hybridize biomass with solar, and you can cover almost the whole energy consumption for thermal use in one building or community. And finally, as been applied also in the LEAF House, we have the thermal exchange as a local resource of the building, because we can both cool and heat accordingly to the season. We can couple the geothermal pipes with the heat pump, and we can get a very high efficiency of the whole system. And we see a wide introduction of these systems in the North European countries, especially in north of Italy, in Germany, and in Austria. And we suppose the price will drop in future, and solutions will be further developed. If you have a water river or a water duct close to the building, microelectric generators are available in the market. Price is around 1,000 euro per electric kilowatt installed. The installation is very easy, and the technology is mostly consolidating, except for the electrical integration, where we think there is a space for improvement, as some specific inverters or way to pilot the generator can be still introduced. These two systems, as I said before, these other systems are combining generation of heat and power, and it's a more effective way to process the gas, natural gas that is available in most of the communities in Europe, but also in other countries. You can use micro turbine generators. The price of them is improving, and wide diffusion can be forecast in next year. You can apply very small cogeneration in gas burners. This is a system that is presently sold in Germany. It's called Lion, and it is using a steam expander together with the water heater to generate 1 kilowatt, I think, in the house in Germany. And you can process, of course, hydrogen with fuel cells. Fuel cells are still expensive, as you tested in this house. It's not fully developed technology. We have problems to handle hydrogen, to store the hydrogen gas. So we are still waiting for full market level solution. I stop and Filippo will go on because I think we have to change a little bit the voice.
Okay. The use of heat can be processed to obtain cool energy, and the equipment used are generally two: the absorption chiller and the absorption sea chiller. In this first slide, the absorption chillers are devices that use an absorption cycle, and it can be used two kind of source, solar, for example, or waste heat, because they can be driven at a low temperature, at about 9 degrees. In the first case, we can use a mixture of water and lithium bromide solution for chilling water above 0 degrees. And instead, other equipment use a mixture of water and lithium chloride, or especially most common water and ammonia, to produce water below 0 degrees. This kind of chillers can be or a single effect or a double effect, increasing the coefficient of performance. That is a coefficient that can be useful to understand the amount of primary energy necessary to drive it. The absorption chillers, we use instead the silica gel or the elite. This kind of product is not still presently widespread in the market, and has a COP lesser than absorption chillers. Works at about 80 degrees, and they use absorption material in solid cycle. The price is still high, and the number of cycles are not at the moment efficiency in the time. So the DEC systems are mature in terms of price of reliability, but not present in the market. There are some sort of intelligent lighting that can be used. For example, in this case, we found new systems to make light inside the buildings. In this picture, you can see parabolic mirrors below the glass cup that introduce the concentrated beam on other mirrors, and the beam is taken inside the building. There are some ESCO that are using this business and are coming out to reduce the overall cost of energy produced instead to make lights inside the building. Other interesting methods to make storage are the electric one. It's very interesting, this picture, because it represents an horizon plug as a flash system that produce at about 2 kilowatt hours of power at about $1,600. 10 Tesla power starts from 3,000 for 7 kilowatts and 3,500 for 10 kilowatts. Those are batteries that can be useful for lithium technology to be used for about 4,000 cycles, and can be easily introduced inside the apartment or inside the building in an interesting way. We have spoken about the kind of thermal storage, the production of energy from the sun, for example, but it's very interesting to understand how a thermal storage can be used to produce after the period of collection of ZEB in new energy. The picture on your right can be useful to understand that in the time from when you have daylight, you can use for the production of energy to satisfy the electric demand, and in part can be used to make storage. This part, the energy, thermal energy storage, can be used after in the afternoon or when the sky is closed, to create another buffer of storage that can produce a plant output most constant in the time. So it's very important for the solar energy systems to have a buffer of fluid, hot fluid, that can be used to drive the equipment as or sea or sealer in continuous way. The typical way to storage thermal energy, of course, is the water, because it's a cheaper way, and it can be used to produce generally domestic hot water and supply it from 500 liters to several cubic meters. This technology is very cheap and very mature, and can be used to store water at about 80 or 90 degrees, coupled with equipment as evacuated solar pipes, for example, or solar panels. To improve the density of energy, we can change the kind of fluid and move to oil or molten salts. This kind of storage, or in particular molten salts, are under development. Other interesting systems to store the thermal energy are PCM, phase change materials, that use the change of phase of some materials. Paraffins, for example, can be used to store for the transition more energy in few space, and return the energy at typical temperature. The melting process involves energy density on the order of about 100 kilowatt hour per cubic meter, for example, the ice, that is compared to the typical 25 kilowatt per cubic meter for sensible storage option.
Yes, just 2 words about control systems, because this topic will be very, very wide to be discussed. There are many players. There are some players that are integrating their offer in the one-stop shop. For example, ABB or Schneider, as you have underlined in the presentation of the LEAF House. I consider very interesting the entrance into this market of big ICT players, as Google did, and most of them are going to enter, because this is suggesting us that the home control system are going to be a part of the ICT family, and this market is going to have the same behavior of the typical consumer electronic market with new business models. Put in the picture the Nest system that is learning about the behavior of the tenants of the building and is suggesting a control strategy accordingly to this. And this system is connected with the internet, and so it can use other data, it can learn from other devices and so on. So it's changing of paradigm in control systems that I think will affect quite much the market in next year, especially the consumer one. Going to end, the zero energy buildings are really at the crossroad of many different markets and technology trends. We have some measure solutions. We have most very interesting innovations that have been addressed in last 10 years, and some of them are going into the market. But we think that the very strong market growth that we will see in next decades will drive all this into a more advanced and more integrated approach where even new industries will be created. The interest of very big players is showing that the building is going to be considered as a technological unit, no more, let's say, old and traditional envelope where you have just to introduce advanced appliances, but the whole building will be a technological artifact. And the most complicated thing is to go into an integrated design and to bring people into this new era with educational and support approach to keep them committed. We need new regulations because the regulations are driving the technology mix. That means that what has been supported by regulation, for example, TV, has gone quite faster and than the other technologies that have been less supported. So the activity at the regulation and political side is quite relevant for that. The combination will depend upon local climate and building culture, and regulation should take care of this because we have regulations at the European level that are mostly oriented by, let's say, North European climate and less by South European climate. So that we need a sort of balance to help a balanced growth in different countries. And we have to take care about the cross-cutting issues. I suggest to underline the aesthetics because we need more aesthetically integrated systems. Safety, we have to consider the whole life cycle when we talk about the environmental impact of new technologies. So we cannot say it is improving the behavior of the building now, but when we have to refurbish it or we have to disassemble it, we don't know how to treat the system. We are going in this direction. That's more or less the same that, for example, the automotive industry did in last 20 years, and we should take some experience and best practice from this. I think that's all, and even if we are in delay, we are quite interested to hear your questions if there are. Thank you.
Hello? Sorry, Professor Kolokocha, we cannot hear you properly. Hi, we cannot hear you very well. We cannot hear the energy group very well.
Hello?
Yes, hi, now we can hear you.
Okay. Thank you, Fabio and Felipe, for this, and also the group of AEA for this very interesting presentation. I wanted to ask one question about the PVs that are installed, the BIPVs, which are, I don't know the slide, but I've seen that there are some colors in this. And I wanted to ask, these colors are available, or is something is rendered via the system?
Yes, I'm going there. I think it's this one, the next one, this one.
Yes.
Yes, 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 they can be produced in this way because they are, the process is like an inkjet coating. So you can choose colors. Of course, if you want to optimize colors, you are losing something on efficiency.
How much do you lose? Do you know?
I think they are around the 5-6% at the moment of efficiency. We are going. These are the glass blocks that should be installed in 0+.
Yes, I know that. But I was wondering because I didn't realize that there were colors.
Yes. You can use a colored film. And you can coat the film with the DSC process. So the color is in the back layer.
Okay.
Of course, you have some. They are interfering with the generation process, but I don't think you are losing quite much. I can check the exact effect of coloring them.
Does this change the temperatures of the photovoltaics? The coloring, maybe with different colors you have different temperatures, and then maybe you have different efficiencies. Is it that correct or no?
Yes, you will change it very slightly. Of course, you are reflecting a different part of the spectrum. So if you reflect the red is better than reflecting the blue, but I don't think that as it's transparency, most of the radiation is getting in. So I don't think there will be a big difference in that.
Thank you, Fabio. Thank you for this.
Hi, I would like also to ask a question. From what I understand, you were involved in the design of the concentrated solar thermal system in Cyprus University or nearby. So I wanted to ask you, what was the major technical challenge in this project?
So the design of these systems is coming from a specific activity with the aim to reduce the focal length. As you can see, we have a primary optic and then a secondary optic that's on the top of the system with the heat, the absorber pipe inside. And usually these systems have a higher secondary optic because the focal length is bigger, and it has been redesigned to reduce it. And the other challenge was to reduce the cost. So to standardize as much as possible the components and to make the installation as easier as possible, because the installation on a roof is not the best opportunity for the cost on the cost side. So this is the most challenging, I would say, problems that we had. In this case, the systems have been made very flexible because each mirror has a independent turning system, so it can be reversed to host a PV on the other side. And this was again a challenge because in this way we needed more actuators, more complicated electronics, and so on. But we think that this is a good system to build integrated roofs in warehouses, in industrial premises, because the collecting systems could be the roof. In the picture you see that we have used an existing roof, but it would be very interesting to create buildings in which the collector is itself the roof.
Thank you very much. This is very interesting. And one last question from my side. Do we have an estimate of the generation costs, as in euros per kilowatt hour production?
It depends upon what you want to produce. For thermal production, yes, they are not far from the traditional systems. So the vacuum pipes, because the price for the square meter of collection is almost the same. It's just 20% more, and consider that the efficiency would be a little bit less because you have two optics. But the enthalpy of the production is quite higher because you go up to 300 degrees. So again, you have to use the right solution for the right problem. If you want to reach a high enthalpy because you want to store in a compact way, so you want to store at 300 degrees instead of storing at 90 degrees because it's quite better. You can, or if you want to use this heat for as a process heat or for solar cooling. In this case, you have a little bit higher cost for thermal kilowatt produced, about the 30%, I think, at the moment, and but you have better energy.
Thank you very much.
Welcome, Pastor. I think there is a problem still from Cyprus.
Sorry, Professor Sergidis, we cannot hear you. We cannot. Sorry, we cannot hear you well.
Hello, to Cyprus, we cannot hear you very clearly. So can you please type something and we can, is it the closing or is it something else that you want to mention? Sorry, Despina, we cannot hear you. Can you please try to write?
Hello.
Hello.
Can you hear us?
Yes.
Yes.
I am Christo from Cyprus University of Technology. We have a question here for IDEA.
Okay.
Hello, my name is Marilena Michailidou. I want to ask you, what are the temperatures that are reached below the solar thermal collectors, and are these temperatures affecting the indoor comfort? Thank you.
Which in one of these, it depends upon the kind of collector. So in the low, the LT, you have 10 degrees above the ambient. Then in here, in the flat glazed panels, you can go up to 50 degrees more. And with these ones, it could be even 100 degrees more. With concentrating solar systems, you can reach 200 or 250 degrees more the environmental temperature. But this is completely uncoupled with the interior of the building, because usually you store this energy in something, maybe the water that you can use both for heat transfer fluid, as a heat transfer fluid, and for storage, or you can use different solutions with oil or other systems. And then you need a system to give the heating or cooling inside the building. So you have to uncouple the two things. If you want to use it directly, of course, it is affecting the comfort, because if you want more than 10 degrees, you cannot use the LT systems because they are not enough. So you have to take care about that. You have to take care about the limits of the collectors, and if it is needed, you have to hybridize the solar source with other things, or to regulate if you are at a higher or lower temperature than the one you need in the building.